Welcome, guys. Yeah, so I forgot to say another implication about the compact. Yeah, so let's see. Yeah, so I previously say that in the Rn dimension, the Euclidean space, there are three things which are equivalent: a constant bound, compact, and every infinite subset of K has at least a limit point in K. Okay, so from here we can derive the theorem, which is called Weierstrass. Okay, so Weierstrass theorem says that every bounded infinite subset of Rk, infinite subset of Rk has a limit point in Rk. Okay, so in a series dimension, in a sequence view, so just basically you given any sequence in the Rk, and it's bounded, then you will have a convergent subsequence. Yeah, so you can maybe when we talk about the convergence of the subsequence, the convergent sequence, then you can easily prove from here. Okay, now this proof is trivial once we once we know that the compact means close and bound if only compact in the Rk, right? Because let's say this set is called E, right? And which is bounded, so I can make a large cube to cover it, right? But this is compact, so every bounded infinite subset of I has the limit point in I, right? So which is definitely inside Rk. Yeah, so proof is almost true. Okay, so let's talk about today's topic. I like this topic. It's basically called perfect set. Yeah, so perfect set means that every point, let's say called P, every point in P is a limit point. There are some very deep theorem about the perfect set, but I think for the analysis we only need the following one. Okay, so theorem: perfect set is uncountable. Yeah, so basically this is I think every analysis proof. This is every analysis textbook talk about this proof. I think the routine 2.4 for C. Yeah, so P is uncountable. Okay, so proof. Also, by P should be non-empty. Okay, otherwise that we cannot say anything. Okay, so theorem. Yeah, so let's give it a proof. Okay, so remember the perfect set means that every point in the P is a limit point. Okay, so basically P is the same as it's the set of meeting points. Okay, so we already proved that the finite set do not have limit point, right? So you can know that the P must be infinite. Okay, so suppose P is uncountable, right? We need to prove that this is a contradiction, right? Suppose P is countable. So that means I can write P as by the way, P should be Rk, subset in Rk. So P is x1, x2, let's say, right? P can be written as a lot of right, keep going. Okay, so yeah, so our P now is xi, right? I from 1 to infinity. Okay, and they are infinite. Okay, so I can construct a ball, right, called Vn for each xn, which is a radius, which is a ball in Rk, such that y minus x less or equal to r. Is equal to r, and I denote the V bar as its closure, so it's the same as previous, just the closed ball. This is xn. Okay, so let me draw a picture. So that means this xn, right? I create a ball called Vn. Okay, so now we will face some issue, right? Because xn is a limit point, right? Every point is limit point, right? So you can find so this whatever Vn you choose, right? There's another point called xn plus 1, right? Sorry, you can find the points. I label it by xn plus 1. So I relabel the number. I denoted for each Vn, right? You can always find xn plus 1 because xn is a limit point. But you can always find xn plus 1 such that this xn plus 1 can create another ball called Vn plus 1, such that xn do not fall into Vn plus, do not touch the boundary and do not fall into this Vn plus 1. Okay, so what I'm saying is that one can construct Vn, right, such that Vn plus 1, such that the first one is Vn plus 1 bar, so it's a closure, falls into Vn, right? See this picture. The second is that your xn do not belongs to Vn plus 1 bar, right? And also, this Vn intersection P is non-empty, right? Because Vn contains Sn and the P contains N, right? So this is obviously true. Okay, so this is just come from the definition. Okay, so what? Yeah, this is for all N. Okay, so once you have this, then everything is trivial, right? You just define. You can easily see so define Kn to be Vn bar intersection P, right? So notice that by definition, your Vn plus 1 bar is subset of Vn. So Kn plus 1 is a subset of Kn, right? And notice that this, yeah, so you can find this, right? So you can see that this Vn bar is closed and bound, right? So Vn bar is compact, and you have this, right? So this is compact. Okay, so from this, you have this, and you also notice that right, now also notice that let's see, yeah, so you have this, right? So and then notice that by definition, right, your xn do not belongs to Kn plus 1, right? Your xn do not belong to Kn plus 1. Yeah, this is from my construction, right? Because Xn do not belongs to Vn plus 1 bar, right? So which tell you that the Xn cannot belongs to Kn plus 1, right? Xn cannot belongs Xn plus 1. Sorry, Xn cannot belongs to Kn plus 1 because I already removed, right? Xn do not belong to Vn plus 1 bar. So Xn do not belongs to Kn plus 1. Okay, so which tell this means that no point, right? Because your P is written as xi from 1 to n, right? So no point of x, no point of P, what lies in all the intersection, right? Kn from 1 to infinity. Okay. Also, notice that this Kn belongs to subset of P, right? So Kn is non-empty. So Kn is non-empty, right? For each n. So you have this and you have this, right? Okay, so by the theorem, right? The previous theorem that we proved, this should be non-empty, right? But the problem now is that you have shown that this is empty, so contradiction. I remember that we have proved. That if you have this situation, right, everything is non-empty, and one each one, which is keep going, then finally it must be non-empty. The intersection must be non-empty. Remember that what we originally say is that Kn must be closed, right? But now Kn must be compact. But now you can see that Kn is compact relative to P, right? Kn is compact relative to P because Kn is compact relative to V. Sorry, Kn is a compact. Kn is a compact relative to P, right? Because Kn is defined to be compact set intersection with P. So Kn is relatively compact to P. So I can forget about original situation where the Kn is compact in the whole K. I only care about Kn is compact relative to P. So this case we get a lot of compact set, such that one eats another and everything is non-empty because it's subset of P. Also, Kn at least contains the Kn at least contains one point called xn in Vn bar, right? So Kn is non-empty, and the one is one. So by our previous theorem, the Cantor intersection theorem, their intersection must be non-empty, right? But since in your construction you prove that no point of P lies in, so you prove this is empty, so contradiction. Okay. Okay, so example, a closed interval in R is compact. So it's perfect. Yeah, this is trivial, right? Because you can check by yourself. Yeah, just talking about Cantor set. Yeah, Cantor set is a little bit it's very interesting. So one can make a lot of video about Cantor set. So I'm going to talk about the thing prove that this is perfect. So Cantor set is that you start from 0, 1, right? And you remove you remove the open interval like this one, right? So in the first situation, in the first cut, you remember it becomes this, right? So the first cut remains this. Okay, and the second cut basically you cut a half, right? You cut 1/3 and it becomes this. Then you keep going. Okay, so obviously you final will got a set called C. Okay, so by the previous theorem, right? This is compact. So if you define the C to be the intersection of all Cn, you also have Cn, it's Cn plus 1, right? So by the Cantor theorem or intersection theorem, what we have proved, everything is compact, non-empty, so C will be non-empty. Also, you use theorem, at least you prove there's a 1 point. There's at least a point, right? Such that Cantor set is non-empty. So what we have proved is that it looks stupid that Cantor set is non-empty. Okay, so this is somehow trivial, right? Because obviously that 0 is always 0 is in each cut, right? Because 0 cannot be cut. So obviously that 0 and 1 should belongs to Cantor set. Yeah, so actually we didn't prove anything results and any important thing, but we also proved that Cantor also from this we know that Cantor set is compact, right? Because it's an intersection of a compact set. So Cantor set is compact. Okay, but we want to prove that Cantor set is perfect. Yeah, so this is the non-trivial thing. These two can be viewed as a trivial, right? Once you know the definition. Cantor set is perfect, and so Cantor set is uncountable. Okay, so usually people talking about Cantor set is uncountable because I don't know if you know that you can write any number 0 to 1 into the 1/3 expression at A0 divided by 3, A1 divided by 3 squared, A2 divided by 3 cubed, and keep going, and then your AI belongs to 0, 1, and 2. And then you maybe you notice that the Cantor set just remove this, right? So you can use the diagonal theorem to prove this is the uncountable, right? But in this video, we use our previous theorem. We prove it's perfect, so we use a theorem, and we know that it's uncountable. Hopefully, it's not difficult. So how to prove this? Okay, so okay, so let's call each of these one called the this small connected interval. I call it segment. Okay. So in order to prove P is perfect. So in order to prove P is perfect, we just need to show that P contains no isolated point. So isolated point means that there's a point P. You draw there's an interval, there's an open neighborhood V such that in this region no other point in P. So this is called isolated, right? So if you are not isolated, it means that whatever we choose, there's an infinite point in it. This is called the limit, right? Limit point. So we just need to prove P do not contain isolated point. Okay. Right. So let's say x belongs to P, right? Pick any point x. Sorry, P is C now, right? So P is a Cantor set. Okay. So if x is in the Cantor set, right? So there must be some segment, right, which already originally covered it, right? And they keep removing, but the x still survive, right? So there is the segment. There is S, which cover x, so contain x. Okay, and so you can create an interval, right? So there is the interval. So let in be that interval, interval. Right, so in means that the n, this is C0, maybe call C1 step, C2 step, C3 step. Right, so in will be that interval in a Cn step. Okay, and what? Okay, sorry. This S can be so this S can be any segment containing X, and then the in be the interval of the Cn step. Okay, so I can choose. So suppose your X, right? Your X is covered by some segment S, right? But in is the interval in the Cn step. So if n is close, large enough, right? This in will shrink smaller, right? So you can, when n close enough, then in large enough, this in will be subset of S, right? So you can let let's do it let your Xn be an endpoint, be an endpoint of in. Okay, so basically what I'm saying is that you pick X, right? You pick, you can okay. So let me just tell you. So one can easily set the endpoints. Right? These endpoints will never be cut, right? So for example, this 1/3 is always in a Cantor set, right? So we only care about the point which is not in the not in the endpoints, right? Because if the point is in the endpoints, then I already guarantee that this is limit point, right? Because whenever I shrink whenever I cut the interval, that interval already always there's always an interval which touch the endpoints. Right? So that endpoint must be limit points, right? So which I only care about the point which is not the endpoint. So for that point which is not endpoint, I contain I suppose that you draw any segment S or any open interval, and I can find such in which is an interval in the Cn step which can arbitrary small and cover your X, right? So and I let Xn to be an endpoint of in, right? So remember that Xn is never cut, never be cut. So whatever S you choose, right? So whatever open neighborhood you choose, there exists an which large enough such that in falls into S, right? And the endpoint of in is called the Xn, right? So this Xn belongs to Cantor set because this is an endpoint. Endpoint never cuts, and Xn belongs to S, right? So whatever points you choose, you can always find and whatever neighborhood you choose, right? There's always a smallest. There will be another point in a Cantor set which very close to you. So X is a limit point. Okay, so every point in X is available. So Xn will not the same X, right? Because my X is not endpoint. Okay, so X is a limit point. Okay, so P, this P Cantor set P or called C is a perfect set, which is uncountable. Okay, see you guys next video. Hope you guys like the channel. Bye bye.